Hello everyone, and here let's start the chapter 8. The chapter 8 is kind of combined loading, and here I kind of skip the chapter 7, which is more circles, and directly come to the chapter 8 first. The reason because I just like to take advantage of say the fresh memories of the individual loading, the stresses analysis for individual loading, and then from there we see when combined the different types of the loading together, how can we do the stress analysis. In these chapters, and basically I would say this is a review of the four the loading types we have learned, and here I'm going to individually going over the four examples here. Okay. Let's start with the first sections and also take a look at the first example here. So the purpose of the combined loadings is to help students to learn the procedures, actually effective procedures, and for analyzing the stress due to combined loadings, combined different types of the loadings. Okay, here for these examples, and here the kind of structural the materials and on the various kind of the loadings. And here, for example, if we want to interested in the stress around the point K or H here, and how can we do it? So that is the purpose of these sections, and here I'm going to give you the steps. Okay, and so that's an outline here. Let's take a look at the detail here. So here before we go to the discussing the combined loadings, and the combined loading basically is from individual types of the loading. For example, in chapter 1 we have learned is the axial loading. So for consider this material Young's modulus and the length L and cross-sectional area A, and under loading say P. So we know this one will induce the normal stress. Okay, so the normal stress will be induced here, and the normal stress basically is equal to P divided by A. Okay, and that is very straightforward. And if tensile, then we use the positive. If that is compressive, then we use negative. That is our sign convention here. In chapter 3, what we learned is a material model is we call this shaft. Okay, for example, here we have these things, and if say you like to apply the right hand rule, so basically this force is in the double arrow system is like this. Let me call this T, torque. Okay, so now in chapter 3 we learn that we induce Shin stress. Okay, the Shin stress, let me say take the cross section here. Okay, so if you are a little small person, let me take the view from this view. Okay, so that in this way, this is the center here, and then the torque is applied in that direction. The magnitude is TR over J. And J, for example, here for say if we consider hollow shaft, and this is the inner radius Ci, the outer radius Co. So J we know is pi over 2, and Co force to the first power, Ci to the first power. Okay. And the distributions of the Shin stress due to the torque basically is can be like this. That is in linear distributions. Okay, and depends on the R. So for example, if you want to calculate what is the Shin stress here and that location, let me change the color here. I want the black one. So for example, from the center to here, if you measure its R, basically the magnitude is TR over J. Okay, and the direction is in the way such that this stress multiplied with this arm will induce a little moment. That moment should be in a line to the direction of the T torque here. Okay, so that is what we learned in chapter 3. In in chapter 4, and what we learn is bending. So for example, we consider prismatic bending the beams. Okay, if for example here we under the bending here. Okay, so here we take the cross section. Let me exaggerate. For example, the cross section will be like this. Okay, so from here you have learned is the first one, you need to identify the neutral surface, and which means on the cross section, the intersection of the neutral surface to the cross section we call the neutral axis. Okay, that is the very first step you need to determine, and also the next one, you need to determine the moment of the inertia of the entire cross section respect to the neutral axis. Okay, so for this case, the bending for these sections, the bending will be like this. Okay. So for these particular examples, then from here you should have learned the upper portion for these illustrations. In particularly for this illustration, upper portions of above the neutral axis is compression, the lower portion is intentions. Okay, and then the magnitude, this one is a bending stress. For this example, the bending stress is in linear distributions. Okay, and the magnitude of the bending stress basically equal to my over I, and I is the one we've been calculated here, and m is the bending moment which is given or determined. So what is y? Y is this. So again, if you're interested in knowing what is the bending stress at this level here, and you simply measure the distance from the level to the neutral surface, we call the y. So from here, the y is the parameters for designers, and that determine, for example, if you want to find out the maximum stress, if you say, for example, I want to find the maximum stress here, then basically you simply pick up whatever the maximum value for y. So for this case, that should be here. Okay, so that is the one here. You can get the maximum value, and that is where the maximum stress occurs. Okay, so and then this is the third loading type. The last one is from transverse loading. So let me take the cross-sectional view directly, and that is what we just learned from chapter 6 here. So this is the cross-section of a beam. Okay, and the transverse loading will induce the Shin stress, and Shin stress basically that is induced by, we call the not pure bending. If the bending is not impure anymore, so we will induce, okay, we will induce the Shin stress, and in that situations, the this is the transverse loading V we calculated. And again, for this case, for given this direction of the transverse loading, if this is a centroid, then this is the neutral surface, sorry, neutral axis. Okay, so once this determined, then the magnitude basically tau equal to VQ over IT here. So what is V? V basically is the transverse loading on the cross sections, so that is calculated or given here. And I is the, again, I is the moment of inertia of the entire cross sections. Okay, and actually I is exactly the one we calculated in chapter 4 here. Okay, what is T? T will be determined by, for example, say I want to calculate what is the stress at here. Okay, I want to determine the stress at here. So that gives you the thickness. The T is the width of the selected cut. Here, for example, I'm interested in determining the stress along this level. So that is the width. Okay, T is the width from here to here. So that's the T. So T is the width of the cut, and now we determine what is Q. For example, if we're interested in determining the stress along this level, then we simply pick Q above the cut. That is the first option. The second option, you can pick the shaded area below the cut you're interested. Okay, either way you simply determine the Q, and Q basically equal to A star times Y bar star. And for example, in terms of the green option, so this is a centroid of the green shaded area, and then this distance is we call the Y bar start. Okay, so that's going to come to here, and the green shaded area has area A star that come to here. So from here we determine the Q here. Okay. So that gives us determine the magnitude of the Shin stress, and then here for the direction of the Shin stress again, along this cut, the direction of the Shin stress should be aligned to the given transverse loading. So if transverse loading is downward, then the Shin stress point downward. Okay, so that is the one we have learned. Now in chapter 8, and we're going to encounter very common and general situations in which the loadings from either this, or all together will come together, and then we see how can we do it. Okay. So let us use this very general example to demonstrate the procedures. Okay, so consider these structures, and here you can see these under various and arbitrary loading, and this can be point loading like F1, F2, F3, or even this can be distributed loading, which is not shown here, but you should assume in general that could happen. Okay, so we got given this one, then here we want to know for example, we want to know what is the stress at point K and what is the stress at point H here. So here is a step. The first one is to, once you are asked to determine the stress, for example, at point K, and then the first step is to you pick up sections that pass the point you're interested. Okay, so you pick this section. Okay, so select a section that passes through the points of the interest, and then the next step is to define the appropriate coordinate systems. Okay, so for example here, on the selected cross section, you identify the centroid and place the origin of the coordinate system in the centroid, and then we define the coordinate system. For example, let me define and say try to align with our textbook. So let me define this as X direction and use your right hand rule. So this is a Y direction and this is a Z direction. Okay, so basically in this case, then point K is on the west side and point H is on the north pole. Okay, and the cross section for this one, this is a circular kind of rounded the shaft. So basically the cross section is a circular cross section. Okay, so that is the second step. Then the third step is to determine in terms of the selected cross section, and we want to determine the reactions there. The reaction including force components as well as the torque or moment like components. Okay, so here we showing schematically and showing in general on this is a selected section here. Okay, and here it didn't draw it, but this is a point K here and this is a point H here. Okay, so in the selected sections, in general, they have 3 loading types and 3 forces components. That means the in terms of our components, that is Fx, the force in X, Y, Z directions. Okay, in general, and what is Fx, and that is a P here. Okay, because in terms of our coordinate system define X, Y, Z. So here the textbook, the purpose of the textbook simply want to convert whatever the symbol convention to whatever we learned from chapter 2, 3, 4, and 6. So in terms of this one, you will know the force component in X direction is the normal force. So we pick the component P. And the force in Y directions, then here basically that is belonging to respect to this cross section, that is transverse loading, so we use V. Okay, the transverse loading in Y direction, and similarly transverse loading in Z direction. From here you can see basically they adopt the notations in chapter 2. Here in chapter 2, here is P, here we're using, so P over A is the stress in, and then in chapter 4, and here that is a V, so here we adopt the V. Okay, so hopefully you understand this one. And then we also have 3 moment components in XYZ direction individually. Okay, so in general, we keep this in mind. And then now let me map to the simple conventions we use. Okay, so now the first one, the moment about the x-axis. So here is our x-axis. The moment or moment-like quantity about the x-axis. So in terms of the selected section here, actually is the torque. Okay, so that reason why here we have the moment in the moment in the x component, and that using this notation t here. Okay, so that is this one. And the moment about y direction, and actually that is the bending. Okay, so here we use the m and in y direction, and the moment in z direction in the similarly, that is a bending. Okay, and then we use this one. So here in this step 3, we have individually schematically and demonstrating the type of the reactions, and this is the most general. So basically involving the 3 loading force components and 3 moment or torque like components here. So now the remaining is based upon the distributions, say this based upon the calculated the types of the different loadings on the section, then we can proceed to determine the stress. Okay, so we calculate the stress in response to individual loading type. Okay, so for example, in terms of the chapter 2 axial loading, you calculate one, and in terms of the V, and here for example this is the Vy, then tau equal to Vq over It, and respect to whatever the point you're interested, and then here we have a tau. So individually we calculate those things, and then we superpose the calculated stress components together. So that is the general procedures. And so here, before we move on to the quantitative analysis, and here let me give you again a general guidance about the what could be in our UC in the calculations. So the normal stress, the first one, the normal stress will be coming from 2 possible situations. One is axial loading P. Okay, so this one will give us the normal stress, and that one actually equal to P divided by A. And in terms of our coordinate systems, and in terms of, okay, so in terms of just like this one, and also the bending my mz. So for this case, we consider the my here. So this is a cross section. So here I'm showing you is this cross section. Okay, so in this cross section, let me label my our coordinate systems. So this is the x coordinate, and this is y coordinate, and this is z coordinate. So this is y z coordinate. Okay, so right now we have the bending my here. So my is the in this sense. So from here you can see the first one, we can identify the neutral axis. The neutral axis is this. Again, if here you still confused why the neutral axis is the y-axis, please go back to the chapter 4 there and to get more detail. Okay, so here you should know already the neutral axis is the y-axis, and then in this case the left portions will be in tension, the right portion will be in compression. Okay, and then the bending stress, basically the bending stress, and say if this is the side view here. Okay, so let me see that this is a side view and this is the neutral surface, and right now the my is given by this. So from here you can see this distribution of the stress is like this. So this one is actually in which directions, and that one, this is our x direction, this is our y directions. So basically the bending stress in terms of our coordinate system defined here, that is mx, sigma x. Okay, and here is a sigma x as well. So now the magnitude equal to my over I, that is our template, and m is a bending here given in y component. And what is y? Y is a distance from any point. For example, if you want to find out this the point here, then this is a distance y you're going to plug in here, and I is a moment of inertia of the entire cross section respect to the neutral axis. Okay, and you can repeat the same thing, the MZ, for example here the MZ, this is the cross sections, and then here is the Y and Z coordinates. Okay, and then let me do this one detail. So MZ is now applied in this sense. So here this is our neutral axis. Okay, so Z axis is our neutral axis. So in this case, the lower portions will be in compression, the upper portion will be in tension. The lower portion will be in tension, upper portion will be in compression. And the same thing, this one, you can see those stress basically pointing out of the papers or inward the paper. So that is the x direction. So the same thing, that is x component and the normal stress. Okay, the magnitude, again, we put into our my over I, this template. And then m is the magnitude of the bending, for this case is z. And y, again, y is the distance from the point interested. For example, here we want to determine the bending stress here. You simply measure the distance, and that is come to y here. Okay, so the distance here come to y, and I is a moment of inertia respect to the neutral axis, and which is the z-axis here. So here I would say this is about the z-axis, and here the neutral axis, which is about y-axis. Okay, so basically the normal stress coming from the possibly will become contributed by the axial loading and the bending. And here I showing is a very detailed kind of schematic showing these things here. And then the next one, we see the Shin stress. Okay, so here I need to erase the things here and give us more space to work on the details. So the next one we're going to see is the how the Shin stress coming from. So basically here the Shin stress is attributed to two things, and the first one is the twisting. Okay, that is our chapter 3 here. Okay, so that is a torque, and that is a torque here. So the magnitude is TR over J. Okay, so that is a one, and if this is the cross sections of the shaft, and if this is the T here, then the distributions of the Shin stress will be something like this. So for example, if you're interested in getting the magnitude of the Shin stress at this point, you simply draw from that point to the center here, and then you make a tangent. So that is the tangent direction to the point in the direction aligned to the T here, the torque here. That is the direction of the Shin. And then the magnitude, basically for this case, if the radius is C, then the magnitude equal to TC over J, for example here. Okay, so that is our chapter 3 here. So this is our chapter 2, and then this is our chapter 4. Okay, and then the another possible the source, the resources, the source. Sorry, the other possible the sources contributing to the Shin stress will be due to the transverse loading. So that is our contents chapter 6 here. So for chapter 6, and then basically yeah, the same thing here. This is, for example, this is our V, and in terms of this is a cross section in terms of our coordinate systems, this is the Y and this is the, okay, so here for this case, let me say this is the VY here. And then taking this one as a Vy, then again we know the magnitude is Vq over I T. This is our template. Okay, and then let's see individually to impose the informations. So here for this case, this is our neutral axis, which is the z-axis. Okay, so for this case, V equal to our Vy given here, and I is the moment of inertia of the cross section with respect to the neutral axis, which is the z-axis. Okay, so I use Iz. And T, now we're coming to say here, if you are interested in finding, say, the stress, for example, along this cut here, then you can pick the shaded area, say like this, and you can determine the Q. Then T simply is the width of the cut measured from here to here. So that basically is the let me use a different color here. So the width simply is the dimension measured from here to here. So that's come to the T. Okay. And then for this case, and I want to identify the directions of the Shin stress. So the Shin stress, again, that should be in the directions the same as the V here. Okay, so for this Shin stress, basically you can see that is the cross section is our X plane. So that is in X plane and pointing to Y direction. So that pointing to the Y directions. Okay, although it is point downward, but still in the Y direction. So this is the component tau xy here. Okay, so now we consider another, so the same cross section here, and then we consider the same cross section, and then the same corner systems here. So now we consider the VZ. So VZ is in these directions here. Okay. So for this case, if VZ is in that direction, so this is our neutral axis. So now for this case, then tau equal to, so let me move here, tau equal to VQ over IT. Okay, so that is our template, and right now I'm talking is this scenario. Okay, so now and let me individually impose the corresponding quantity. So V is the transverse loading for this case, so that is VZ here, and I is the moment of inertia of the entire cross section with respect to the neutral axis, and right now here that is the y-axis. Okay. And now T, for example, say here you're interested in, say, knowing the stress at this point here. Okay, so now you can pick the cut. For example, you take this cut, then this is your shaded area you can pick, and that is for Q. Then what is T? So this T is the dimensions, and dimensions is the distance, the basically from here to here. Okay, so that is the T here. And now in terms of the directions, and direction again, the distribution of the Shin stress must be in the direction of the V here, so that should be pointing to here. And so for this case, you can see the Shin stress is in X plane and pointing to Z direction, so that is the component tau xz. Okay, so from here you can uniquely individually from picking up the techniques we learned from individual chapters in the past, I would say half of the semesters here already. So you should be able to identify and know how to calculate the magnitude of the stress, and as well as identify the set directions of the stress components. Okay, so here for everything, for anything about the individual stress components, if you have any confused part still there, then please go back to the lecture slides and then the lecture videos to find out the details here. And so from here you can see basically the chapter 8 is a very high level and rigorous summaries of what we have learned so far. Okay. Here, once we obtained the calculated stress, then we can go to calculate its principal stresses, which means the maximum stresses and minimum stresses, etc. And those are the topic in chapter 7. And then here, let me skip off this one. But for those who have learned chapter 7, then you can spend a little bit time in this slide. Okay, see what's going on here. Okay, but let's skip off this one here. And let's look at the first example here. And these given numbers. So here we consider a cantilever beam. The beam is made of the I shape. Actually, is this one. Okay, that one you can see from appendix C here from our textbook. Okay, for detailed information. But basically, that is summarized here. The moment of inertia and is I. Okay, I will identify what is that one. And the sec S is a section modulus, and that one equal to this one. So for this case, we simply want to know, we pick the cross section AA prime, and then we want to determine the stress. We simply want to determine the stress at B here. So basically here we want to determine the stress at B here. So that is our goal. So the step one is to determine the reaction including the force components as well as the torque or coupled components here. So we take the free body diagram including the section AA. Okay, so that is the section AA here. Okay, so A prime. And then from here, this is for this simple case, we can very quickly knowing, okay, in terms of reaching the equilibrium, the VA equal to 160 and MA equal to 160 multiplied with this arm equal to this one. So this can be easily done for this example here. So with this one in place, then we can begin to step 2, individually calculate the stress components. So from here you can see, let me put into tabulations. So here we have the loading type, and then we're going to calculate corresponding normal stress or Shin stress, depends on the loading type. So here we have a loading type. The first one is a force, and that is VA here. Okay, and then this is a transverse loading. And we know transverse loading didn't contribute any normal stress, so not available. The Shin stress, basically we know the Shin stress has a template is going to VQ over IT. So that is the template. And now again with this template, let me impose the detail. So for example here, we can see the cross section from this viewpoint and then come to here. Okay. So for this case, VA is here. So let me impose the VA. So VA is pointing from upward, pointing upward. So this is VA here. Okay. So once we have a VA being determined, then we have to determine the neutral axis. For example, this is the centroid of this I-shaped beam, and this is the neutral axis. Neutral axis passes the centroid, and neutral axis is perpendicular to the direction of the transverse loading. So that is the base upon which we determine that is the neutral axis. Okay. So in this case, the I is the neutral axis. Okay, so here I want to specify this about the neutral axis. Okay, and then from here we first determine, so the V here, let me put into the color here. Oops. So from here, this case, and we know the V equal to V here, 160 kilonewtons here. And I is about the neutral axis, and which is given here. Okay, so I is given, and now the Q. And here we're interested in determining the stress at point B here. So here that's very natural. We pick a level containing point B. So that's a level here. So based upon which we can determine. So it seems here I determine the stress, the Shin stress first, but that's okay. So from here we pick up the shaded area here. Okay, for Q. So basically Q will be equal to, for example, the area equal to 206 millimeters multiplied with the 12.6 millimeters. Okay, that's the dimension here. And multiply with Y bar. The Y bar simply say the centroid is the middle here. So simply measure from the middle of this to here. Let me take a peek of the one here. So that's 96.7. Okay, so times 96.7. So that's a Q. And so here we determine the Q here. And what is T? T simply is the cut here. So that is the width. Let me use the different color. And T is here. T is a dimension from here to here, and actually is 7.87. I obtained from this dimension here. Okay, so from here you can determine the whole magnitude here very easily. And then what is the direction? So direction is the Shin stress should be like 1. Okay, so this is, for example, say let me take this is the X direction, Y direction, and so that means this is our Y direction. and z direction. So this is the tau we've been calculated is this one is tau in x plane and pointing to y directions. Okay, so that is the one here. Okay, so that one, let me show that here. Okay, so about the normal stress, so here let me erase the kind of scratch and then see. So now again here I tabulate the calculations. Okay, so you can see here. So now for the second one is we have done this one. Now we work on this one. The second loading type is MA, and that is a bending moment. And we know the bending moment contribute nothing to Shin stress, so this one is not available. So now for this case, we know the magnitude equal to my over I, and that is our template. So let me move the calculation to here. Okay, so in which, and let me erase this portion here. Okay, so now the bending basically is this, and you can see the bending right now is kind of the curve down the whole beams. Okay, the section, the cross section like this one. So basically from here again, if the bending apply in this way, then right away you should know this is the neutral axis. Okay, and the neutral axis about which that's a symmetric plane, and that's the neutral axis like this. So given bending is to curve down, so that means the lower portions will be in, if that's going to curve down, the lower portion will be in tension. Then the upper portion will be in, lower portion in compression, upper portion will be in tension here. So this one really right away you can identify the normal stress at point B here should be in tension. Okay, let me designate that should be in tension. That is determined by this. And now we determine the magnitude. And the magnitude is M, and here we're given MA. Okay, so M equal to MA equal to 60. And y, what is y? Y is the distance measured from the point to the neutral axis. So basically y is the distance here, you need to pick it up. Okay, and that one basically by reading this information is 90.4 millimeters here. Okay, and what is I? I is a moment of inertia respect to this axis. Okay, and that one is actually equal to this one here. So I equal to that one. So with this one again, and you can determine the magnitude, and again this is in tension. So basically this is this magnitude here, and this is from our textbook, and but you need to know that is in tension. Okay, so that is the very simple example to demonstrate the combined loading, and we will see the other three, possibly three other more examples, and that is for this section.